Hello and welcome to the second night of Shackleton's Antarctica NOW Festival. My name is Rachel Halliburton and I'm the curator. Last night we were lucky enough to have Professor Klaus Dodds kicking off the festival with his fantastic overview over who wields power in the Antarctic. If you missed it, you can catch up with it on our website. Tonight we have another great speaker for you. It is Dr. Mark Drinkwater from the European Space Agency. We've invited him because there is a long-standing connection between the Antarctic and space research. It applies whether you're looking up or looking down. Large zones of cold, dry and stable air and the months of darkness make it the ideal place for putting everything from neutrino detectors to telescopes. Conversely, satellites have revolutionized the way that scientists have been able to monitor a landscape that is 1.5 times the size of America, transforming understanding into everything from its ice patterns to its penguin population. Dr. Mark Drinkwater is head of the European Space Agency's Earth and Mission Science Division, which means that he is one of the top people in the world for interpreting what satellites say to us. One of the most critical aspects of what the European Space Agency is doing in the Antarctic is, of course, monitoring climate change. Some of you may have seen the headlines in today's newspapers, which say that ice sheets are melting at a rate that match experts' worst predictions. It's a particularly sobering reminder of why the Antarctic means so much to all of us. Now, we want you all to get involved with the discussion, so please don't hesitate to ask any questions on our Zoom Q&A function. And for now, I'm going to hand you over to Dr. Mark Drinkwater to talk about the work he does, the science behind recent predictions, and how it might shape our response.
Thank you very much indeed, Rachel, and welcome, ladies and gentlemen. Thank you very much for putting your trust in me, for spending your evening in this lecture. My name, again, Mark Drinkwater. I work for the European Space Agency now for over 20 years. But as Rachel said, I've split my career between NASA and ESA. By background, I'm a polar scientist. I studied at the Scott Polar Research Institute at the University of Cambridge. And that's the point at which I went to work for the NASA Space Agency. I worked there on developing satellites, which are specifically designed for measurements at the poles. But today I'm in a more general role and responsible for scientific activities at ESA in relation to their fleet of Earth observation missions in general. And what we do is we try and prepare the satellites to ensure that they deliver scientifically relevant information and that they address some of the biggest science questions of today. So today I'm going to talk about taking the pulse of our home planet, and I'll just introduce the opening slide so I can talk from there. Hang on one second, if you allow me to share my screen, and then I'll bring the slides up. I go full screen. Can you confirm, Rachel, that we're all good with the slides on the screen? Yes, I guess we're good to go. So checking the Earth's pulse at the poles from space, are there signs which are cause for concern? That's the title of the talk today. I'm going to use information collected by our satellites. These are satellites which orbit our planet and crisscross the polar regions many times a day. And this gives us the ability to monitor changes on a broad scale. Satellites, of course, provide us with this unique perspective of the changing face of Antarctica. What I'd like to do is to illustrate the changing face of Antarctica using a variety of satellite data sets. But first, a little bit of background. Our climate record of greenhouse gases from satellite data from 2003 until the present day captures the change in carbon dioxide and methane in the atmosphere. Here in the plot, the blue line shows the column content of CO2 molecules with the values on the left axis in parts per million. And on the right axis, we have methane, which is tracking the orange curve with values on the right in parts per billion. Now, both show a steady increase and a rise over the 2000s since the satellite records began. Now, the consequence of these greenhouse gases is, of course, that the atmosphere of the Earth is warming. And I show you a trend in the next chart, which shows the increase in global average surface air temperatures. This plot indicates the corresponding warming trend by plotting the difference between present-day surface air temperature and the pre-industrial average air temperatures from the period running from 1850 to 1900. And the colored lines that you see here represent the meteorological station measurements and several other reanalyses data sets, all of which indicate a consistent trend. Now, the average global temperature in 2020 was 1.2 degrees Celsius above that pre-industrial level. Of course, the most apparent thing is that the recent most decade is the warmest on record, and this indicates a very persistent long-term warming trend. The warmest 6 years have all been since 2015, and you see that 2019 and 20 top the list with indistinguishably small differences in the temperature rise. Importantly, however, high latitude meteorological stations show that air temperatures are warming at 2 to 3 times this global average rate of increase in air temperatures. And as a consequence, the ice is suffering irreversible changes. And so the subsequent examples I'd like to use to illustrate exactly what's going on from the satellite perspective. But first, just to recap, at the World Economic Forum, a global risk report has been produced by the world's top decision makers, and they place extreme weather events and the failure to tackle climate change as the two top risks. And so inaction to address greenhouse gas emissions is having an irreversible impact on the polar regions and Antarctica. And so the examples I'll show are some of the consequences of increasing emissions and the inaction to do something about climate change. Here's an illustration of some of the tools that we use. These are just some of the wide variety of satellites which ESA is developing or has developed for use both in polar research and studies of the Earth system in general. I show 4 here just as examples. Number 1 at the top left is Cryosat, and I'm particularly fond of this satellite, which has been operating now since 2010 for a decade. As the name suggests, Cryosat was designed specially for precision measurements of the cryosphere, and this includes monitoring the polar ice caps with their elevation and thickness. I'll come back to examples from Cryosat in just a moment in more detail. The other satellites, starting with number 2, are Copernicus Sentinel-1. This is part of the European Union's Copernicus program, and this is providing all-weather, all-year-round radar imaging in day and night. The satellite at lower left in number 3 is Sentinel-2, which is also a Copernicus satellite with optical imaging devices. Of course, optical cameras rely on sunlight, and therefore these instrumentation are useful for capturing changes during the austral summer period in Antarctica. And then finally at lower right, another important piece of this quartet is Copernicus Sentinel-6 Michael Freilich, which was launched very recently at the turn of last year. This is carrying a radar altimeter, which is quite similar to Cryosat, but its focus is to make precision measurements of sea level around the globe. And so we'll show how the measurements from these satellites can be put together to understand not only the changes in Antarctica, but the consequences for sea level. So here's an illustration which shows how our polar orbiting satellites work. The graphic shows the principle on the left of polar orbiting satellites. Each satellite's in an inclined orbit with respect to the equator, enabling us to build up measurements over time as the satellite revolves around Earth. What we see for a typical polar orbiting satellite is that the Earth is turning beneath the orbit plane. The orbit is fixed with respect to the sun, and that's because we like to generate power from solar panels collecting energy from the sun, and they like to maintain their orientation with respect to the sun. That gives us power to operate instruments. Now, we have a fleet of satellites which are in this typical orbit configuration, and this gives us the opportunity to monitor the poles many times a day. And because we pass over the poles 14 times a day, this gives us multiple opportunities to start building up a record of the changes. Now, the typical tools which we like to use on these satellites are microwave radars. This gives us the biggest advantage because of their capability to collect data day and night around all parts of the orbit. The additional advantage, of course, that radars in the microwave wavelength range can penetrate through cloud, and consequently this gives us the opportunity to monitor Antarctica 24/7 all year round. And so I'll illustrate now some of the examples from these typical polar orbiting satellites. Cryosat, the first satellite I mentioned, is measuring the topography of the ice sheet. We remove the ice here to give an illustration of how the Cryosat satellite collects its orbital information. Each one of these stripes is an elevation or cross-section of the ice sheet along the trajectory of the satellite. Its radar altimeter is sending a pulse down to the surface. This makes a very precision timing of the time it takes for the echo to return back to the satellite. And because we know the height of the orbit in altitude, we can use that timing to tell us the height of the surface of the ice sheet above sea level. So what we've done here is to put together an elevation map of Antarctica. We can represent that as a digital elevation model, which is shown on the left. This digital elevation model at 2 kilometers resolution of the grid is made up of approximately 250 million measurements from Cryosat, and we've put that together in a computer representation here to illustrate the three-dimensionality of Antarctica. We can also make a flat representation of the elevation here, and this is a typical contoured map, which shows the highest part of East Antarctica in blue tones, where the surface of the ice cap rises to around 4 kilometers above sea level. On the right, we see a time illustration of how we can use the changes of that elevation mapping through time to look at change. And that's another important attribute when we want to look at how Antarctica is changing. You can see tones in the right-hand panel, which are red, signifying loss of ice where the surface elevation is going down. And we can see parts of Antarctica which have slight blue tones, which are minor in regional extent, which illustrate where the surface is going up because of accumulation of snow and net gain in mass of the ice sheet. But the most important areas where we need to focus our attention today are the areas shown in red and black. These show the most dramatic changes, and I'll go into some detail now about where those regions are and what's actually going on. But first, as a second introduction to the nature of Antarctica is, Antarctica is a very dynamic place, contrary to what we knew from the International Geophysical Year measurements, which were made at locations throughout Antarctica, but which didn't give a perspective for things like how the ice sheet was moving as a whole. Now, the satellite measurements which we have been putting together here allow us to piece together billions of radar data points from the satellites as they're flying over. And this gives us the opportunity to piece together between pairs of images the movement of the surface. We see that Antarctica is flowing. It has a huge network of glaciers which drain and transport ice under the force of gravity over distances of thousands of kilometers from central Antarctica towards the coast. And this pole to coast representation is the first time we've ever been able to piece together this kind of a view of the dynamics of Antarctica. You can see rivers of ice cutting from the central part of Antarctica down to the coast and delivering ice to the ocean, where it's lost as it crosses the grounding line and becomes floating and breaks off as icebergs. And so this is the process driven by gravity, which is forcing ice from the central part of Antarctica to the coastal periphery. And that's an important background to the next charts. On the left here, I'm showing a static representation of those dynamics as ice sheet velocity or speed of the ice in those ice streams. This shows a scale from 0 to 10 meters a day, where purple and reds show the fastest moving ice in some of the largest ice streams. Now, the important thing to note is that ice dynamics have an important control on surface elevation of the ice sheet by export or redistribution of ice. And in places where ice mass is not replenished by snowfall, there's a net removal of ice mass, and this results in the deflation or the lowering of the ice sheet surface. And we see on the right chart the surface elevation change cumulatively over a period of 5 years between 2010 and 2015. And we see orange regions which correspond to the regions of the strongest flow in West Antarctica, for instance. If I point to some of the dominant regions of interest, here in Western Antarctica, we can see the Pine Island and Thwaites glacier basins. And in the cryosat elevation change maps, we can similarly see these orange tones where the surface is going down by more than 10 meters cumulatively over that short interval of time. And so what we see here is the surface effects of ice movement in our radar satellites, which illustrate the close relationship between the dynamical changes and the surface elevation. This gives us clues about where the surface mass is moving, and it tells us where significant changes are ongoing. Now, if you look at the perspective generated by Cryosat over the interval 1992 to 2019, here on the left panel, we're showing the elevation change in this movie representation showing the interval from 92 to 2020, which is the satellite interval over which we've been monitoring the surface elevation using radar altimeters. And on the right, we see the calculation of the sea level contribution in millimeters contribution to global mean sea level. We can see that the areas in West Antarctica where there are red tones signifying deflation in the surface are the largest contributors today to sea level by transfer of ice mass from Antarctica into the ocean. And the right graphic shows that over that time period, the corresponding sea level contribution has been accelerating over time. And that's an important signal that we'll come back to in later charts. But let's look a little bit more in detail about what's contributing to this type of situation, because I would like to show a movie now and an animation which shows and illustrates the process which is thought to be destabilizing the West Antarctic ice sheet. Now, circumpolar deep water, which is relatively warm water with respect to the melting point of ice, finds its way beneath the floating ice shelf. It finds its way onto the continental shelf and permeates this subglacial cavity beneath those ice shelves, which fringe West Antarctic coastline. This process is thought to be accelerating the melting at the base of the floating ice, and it's causing recession in the grounding line, which is the point at which the Antarctic ice sheet is rooted to the basal bedrock. What we see is that that's forcing a retreat in the grounding line. Now, if we look at that in a separate graphical sense, what we can see here in the left chart is the way in which the Cryosat satellite is viewing that geometrical change, both in the elevation and the thinning of the ice shelf. So the melting by the warm circumpolar deep water is eating away at the underside of floating ice shelves. And this results in the recession of the grounding line as represented in the graphic on the left here in the animation. Now, on the right, we show a pictorial view of that process. And what I show in the tones around Antarctica are colors representing the ocean temperatures and the proximity of warm water to the coastal ice shelves. Particularly in West Antarctica, we can see red arrows pointing inland, which is showing the rate at which the grounding line is receding. So West Antarctica is often referred to as the soft underbelly of the Antarctic ice sheet. And this, the reason for this is that bedrock topography over parts of West Antarctica are up to 1,500 meters below present sea level. And that's because the ice sheet's depressed the surface of the lithosphere. And also it means that we have a retrograde bed which slopes downwards beneath the ice shelves. So as the warm water erodes the base of the ice shelf, the grounding line migrates inland, and warm water is able to access further and further inland beneath the ice sheet. Now, this is thought to be destabilizing West Antarctica, and the concern, of course, is that this so-called marine ice sheet instability is forcing an acceleration in ice mass losses in West Antarctica. And so essentially West Antarctica is losing grip, and we believe that there are feedback processes underway which can cause the mass losses from West Antarctica to start to accelerate towards the demise of that part of the ice sheet. So in the next chart, I show some illustrations of the glacier flow in those two important regions of Antarctica, Pine Island Glacier Basin and the Thwaites Glacier Basin. Here we see a beautiful movie from Steph Emmett. This is monitoring from the Copernicus Sentinel-1 mission between 2014 and 2020. And the animation shows the motion of the ice stream, which is delivering ice to the floating part of the ice shelf and breaking away in as large icebergs. Now, the animation illustrates the frequency of some of these iceberg carvings over that short interval of time. But the most important thing is the three boxes, which are illustrated as P1, Pine Island Glacier 1 and 2, and T1, Thwaites Glacier. Here on the right, we see a zoomed region of those three zones. And what we see is that the telltale signs of increasing amounts of damage on the floating part of the ice shelf, which is the region contained within this orange line, which is signifying the current location of the grounding line as we speak. What's going on as the ice shelf recedes through carvings is we're also witnessing increasing amounts of damage in these zoomed regions. The damage is contributing to instability in the ice shelf, and as the ice shelf thins and the damage increases, it's having an impact on the structural integrity of the ice shelf. And that leads us to believe that carvings in the future could lead to an even greater recession of these floating parts of the ice shelf in the Thwaites and the Pine Island Glacier regions. Let's turn our attention to another part of Antarctica for a moment, largely because I want to contrast some of the processes between different ice shelves and to show you what's going on further north on the Antarctic Peninsula. I'm going to switch attention to Larsen Ice Shelf here, where we're also monitoring with our Sentinel-1 radar satellite. The Antarctic Peninsula in recent decades has been warming more rapidly than the rest of the Southern Hemisphere, and the northernmost ice shelves experience widespread melting in summer, leading to melt ponding and flooding on the surface of the ice shelf. Now, this water has a tendency to drain into fissures or fractures in the surface, and it feeds a series of subsurface aquifers. It's thought that refreezing of water in the fissures leads to a process called hydrofracture. The analogy would be if you leave a water bottle, a glass water bottle outside in freezing temperatures, of course, the expanding bottle as the ice freezes and expands can burst the bottle. And this is thought to be responsible for the type of fracture patterns that we begin to see on ice shelves like the Larsen Ice Shelf. Now, a fissure had appeared in the Larsen Sea several years before the image time series that we show here. But the fissure and the fracture that had been observed seemed relatively stable until around January 2016, when the crack began to lengthen. Throughout 2017, from January through July, the rift extended to a total length of about 175 kilometers before a rapid event shown in the time series of images here, where the fissure extended and joined the front of the ice shelf, leading to the separation of Iceberg A68. And that took place on 12th of July 2017, when the ice shelf finally broke away. Here we see a static image of Iceberg A68 as it broke away from Larsen Sea, and this was captured by Copernicus Sentinel-1. Now we have a wonderful opportunity to track what a large floating object does after it's been separated from the Larsen Sea ice shelf. You can see the location on the left where the iceberg parted company. This time loop here through 2017 through early 19 illustrates the iceberg bumping and pivoting around before it managed to escape from a grounded region, which you can see chipping away as the iceberg bumps on the submarine topography. We're able to follow the iceberg in time and watch where large icebergs like A68 go. On the left in the chart, we map the positions of the iceberg through time. You see the red iceberg pictorially represented along its course from July 17 through the very recent past off South Georgia. This map allows us to show the course of the iceberg with respect to historical iceberg tracks. I've used a database here in the illustration, which has been capturing the track of large icebergs over the course of the last 25 years. And we can see that this followed a well-worn course following the slope of the sea surface and the currents in the Western Weddell Sea. Now, we're able to monitor the iceberg breakup and the changes in the dimensions of the iceberg over time. And the animation at the top left here shows iceberg A68 thinning and breaking up into smaller pieces over time. The color scale indicates the keel depth of the iceberg relative to the original surface of the iceberg, and we can watch the temporal changes by repeatedly crossing the iceberg and watching the changes over time. And at the University of Leeds, scientists have used the cryosat data and the elevation of the iceberg to map in this way the change in the thickness of the iceberg together with its area change and volume over time. And if you look in the central panel, we can see a series of breakups of the iceberg, which have led to subsequent decrease in the surface area of the iceberg. We can see a corresponding change in the elevation of the iceberg above sea level, which allows us to map the thickness change by converting the height into the overall thickness based upon the density of the ice. And in the lowest chart here in the center, we see the change in the volume of the iceberg estimated based upon the thickness and the area over time. Now, A68, of course, has been a poster child for the demise of ice shelves in Antarctica, but it's not the only iceberg that's out there, and cryosat can be used to pinpoint icebergs throughout the Southern Ocean. And the chart on the right-hand side, courtesy of Jean Tournedre here, is showing the densities of icebergs around Antarctica, which are freely floating in the Southern Ocean. And this plot shows the detections of the iceberg and where the density of icebergs is greatest. And you can see that there's a significant density of icebergs around Western Antarctica, where we've been watching the demise of some of the West Antarctic ice shelves. So let's recap some of the changes which are ongoing and turn to a summary of what's going on with ice mass loss. I show an animation here which captures the changes over time in a study which has been undertaken by ESA and NASA called IMBY. And what we're showing here is the net contribution of different parts of Antarctica and the sum total of the losses of ice translated into sea level contribution. This study from IMBY has shown that when we combine all the satellite observations together, we observe that Antarctica lost nearly 3 trillion tons of ice. That's approximately 3,000 billion tons or 3,000 gigatons of ice between 1992 and 2017. This corresponds in the chart here to the total sea level contribution of around 7.6 millimeters over that course of time. Now, over this period, ocean-driven melting has caused rates of ice loss from West Antarctica to increase. And we see in this summary that the ice loss has been accelerating between the 1990s and the 2010s. So if you make a comparison between the rates of ice loss between them, what we see is that ice loss from West Antarctica has increased from 53 billion to 159 billion tons per year. Now, we also see that the Antarctic Peninsula's ice mass loss has increased and accelerated from 7 billion to 33 billion tons per year. And so what we're seeing is an accelerating trend in the amount of ice loss per year. And that features very importantly in the contribution from not only West Antarctica, but Antarctica as a whole to sea level. So how much is 1 trillion metric tons of ice? If we think about 3 trillion metric tons of ice, what does that look like? Well, when the Antarctic ice losses are added up, we see a total of approximately 3 times the ice cube that's represented here in this graphical illustration. What we're looking at is a representation of a cube of ice, 10 kilometers by 10 kilometers by 10 kilometers on New York City. And you can see it casts a shadow over the majority of Manhattan. Obviously, importantly, today, Antarctica remains a relatively small fraction of the total ice loss around the globe. And that's something that I want to reiterate. Antarctica is still only contributing 3 trillion tons of ice. By comparison to the world total ice loss of closer to 28 trillion tons of ice. Now, if we add together all the glaciers, all the ice caps, and all the contributors to melting ice to sea level, we arrive at a total of 28 trillion tons of ice loss over the interval of the satellite record. Now, this is equivalent to an ice sheet of around 100 meters thick, covering the whole of the UK. So, what does sea level rise look like? I'd like to go and present some arguments now about the contribution and the manner in which it's influencing sea level rise in general. Now, ice mass loss and meltwater that enters the oceans from the grounded part of the large ice sheets raises sea level. Our 28 years of continuous measurement data, like from Cryosat, which is illustrated in the pink part of the curve on the left, gives us this long-term trend in the global mean sea level. We make measurements with our altimeter-based instruments around the globe. This allows us to pictorially represent sea level anywhere on the globe, and we can make an average, a global average of the mean sea level at any instant in time. That allows us to monitor the trend. This shows an overall trend of 3.2 millimeters per year. And this is comprised from the different colored curves here, each of which signify a piece of the record, which has been put together over the 28-year interval by one or another of these satellites, ranging from TOPEX through Cryosat, and more recently Sentinel-3. Now, this record shows that sea level has risen on average around the globe by around 8.5 centimeters over this interval of time. But notably, over the 100 years before 1990, tide gauge measurements around the globe indicate that sea level only rose 10 centimeters. So the rate at which sea level is rising has accelerated due to the combination of a variety of factors, not only melting ice, but also ocean warming and thermal expansion of the ocean surface. And it's that contribution together with the ice mass loss, which is resulting in the sea level rise. Now, what we mentioned at the beginning and what Rachel said was, importantly, our concerns are a consequence of the fact that we noticed that the ice mass loss in West Antarctica in particular is accelerating. Now, we see that sea level is also accelerating due to increasing rates of ice loss. That's plotted in the gray curve is the data here, which we've taken from the earlier charts, and we've plotted on that gray curve on top here of 3 predictions of sea level rise, which are depending on the 5th assessment reports, emission-driven predictions, where we have the upper level emissions of greenhouse gases. We have a mid and lower level of emissions of greenhouse gases. And importantly, the results from our INVI study, which count the mass loss from Antarctica, show that the satellite-based estimates of sea level rise are tracking this worst case climate prediction of ice loss and sea level rise. Now, should the rate of sea level rise continue at the current rate, we're looking at projected additional sea level contribution of over 6 centimeters by 2040. 6 centimeters from now. And by 2100, we're looking at a further increase of up to 17 centimeters, contributed solely from the large ice sheets. So what's the consequence of that? Because I live in the Netherlands, of course, the Netherlands is under threat because it's one of the lowest lying countries in Europe. At the Hook of Holland, near the entrance to the port of Rotterdam in the Netherlands, tide gauge sea level measurements since the 1860s indicate a rise of around 35 centimeters. Most of the Dutch tide gauges, like the Hook of Holland, are currently reporting rates of between 2 and 3 millimeters a year. Now, as one of the lowest lying countries in Europe, the Netherlands is obviously under increasing threat of rising sea levels. And one thing that has been done both to protect the port of Rotterdam is to build the Maasland storm surge barrier, which you see on the right, and the Oosterschelde Kering storm surge barrier on the left. These help to protect the country from rising sea levels. Now, my home is roughly half a meter below sea level in the purple zone. And so I'm particularly concerned that we maintain the capability to monitor, particularly the contribution from the ice sheets to sea level. But satellites can help inform adaptation policies as well. And there's a wide variety of adaptation policy necessary, particularly for low-lying countries around the world, and especially for the countries without the resources to build massive sea defenses like the ones in the Netherlands. So satellite data can be used to inform policy by mapping the lowest lying land, by mapping the bathymetry and the tidal range, and the tidal range under different storm surge scenarios. This allows us to map risk around the coastline, and you can see that the adaptation response may vary depending on the type of land and the population density near the coast. But the Netherlands have done an interesting study to look at the potential of sea level rise around the coast of the Netherlands, and Deltares have made an interesting projection of the working life of fictitious adaptation measures around the coast of the Netherlands. And one of the things that they do is they nourish the beaches and build dikes to cope with sea level rise. Now, the Netherlands is on course with the observed rate of increase in sea level to an increase of around between 30 centimeters and 1.2 meters. And that's illustrated by the brown and dark yellow tones. But the concern, as we've illustrated, is that sea level rise is actually accelerating, and we're actually tracking the worst case climate scenario, which is illustrated by the upper yellow envelope here. And what we see is that if you replenish your beach and plan for a half a meter sea level rise, in the past, your beach nourishment would have lasted for 65 years for half a meter sea level rise. However, with the accelerating sea level rise, if you've planned for another half a meter sea level rise, which by 2070 may be up to 1 meter sea level rise, then the beach nourishment will last a much shorter interval of time. And with further increase and acceleration in sea level rise, subsequent beach nourishment might last even less time. The consequence of that is greater amounts of earthworks are needed, and the cost of beach nourishment and earthworks starts to increase exponentially. And so we do need to be able to predict the rate of rise of sea level, and that fundamentally depends on monitoring of the changes in the polar regions. So to conclude, I'd like to show regions and populations around the world which are also impacted by the consequence of sea level rise. And if we look here at the regions around the globe impacted, it's estimated that 1 billion people now occupy land less than 10 meters above the current high tide line. Now, this includes 230 million below 1 meters above the current high tide line. And recent work has been done to put together a digital elevation map around the coastline of the world from satellite data, and to combine that with population density maps. And this beautiful piece of work by Culp and Strauss provides this combination of information, and it indicates that roughly 250 million people presently live on land below the projected annual flood level around the coastline. And as soon as sea level rises, of course, more and more people get impacted, with up to 350 million people impacted by annual floods by the middle of the century, and potentially up to 630 million people for those who live on land below the projected annual flood level by 2100. And so in this map, we can see that areas around the globe are impacted by this, by sea level rise. We see that Bangladesh, much of Southeast Asia, is under threat from rising sea level. So at this point, it's clear that we urgently need a globally unified effort to curb greenhouse gas emissions and to move to a carbon neutral future. And this is necessary if what we want to do is to mitigate and limit the ice mass losses and corresponding sea level rise. So if you'll allow me, I'll sum up. This is a synopsis from the talk. In the last 30 years, satellites have evidently become one of our critical tools to monitoring the polar regions and the climate change impacts and the changing face of the polar ice caps. And what I've done here today is to try to illustrate how Antarctica is suffering from these changes. We see significant ice mass losses, particularly in West Antarctica and the Antarctic Peninsula, due to atmosphere and ocean warming. The disturbing fact is that current mass losses exhibit an accelerating trend. This is a combination of ice dynamics, surface melting, and the destabilizing influence of the oceans by ice shelf basal melting, which is both weakening and damaging the ice shelves, which help fringe and protect the ice cap at the moment. Now, the corresponding rates of sea level rise are presently tracking a worst case scenario, and that's an important reminder that what we have to do is to plan for the future with effective predictions that allow us to mitigate the consequences around the coastal regions that I've pointed to as being the highly at risk countries. Now, immediate reductions of human emissions of greenhouse gases are necessary to limit further increases in global temperature. And of course, we'll be watching the consequent ice mass losses and the resulting sea level rise with our satellite tools. I hope I've convinced you that we've equipped ourselves both to monitor and predict the future changes. And I think you'll agree that satellites are an essential ingredient to understanding how to predict future changes. So I'll leave you with this thought. Thank you very much for listening. I think it's clear that scientific knowledge is crucial to adaptation and mitigation of climate change in the future. And this focus on Antarctica has been a privilege, and I hope I can entertain questions. Thank you very much.
Thank you so much, Mark Drinkwater, for a really revealing and brilliant talk. I particularly enjoyed the animation of the dynamic Antarctic ice sheet. Now, we have several questions lined up for you. The first one is from Sebastian Copeland, who is the celebrated polar photographer and campaigner, who we're feeling very lucky. We'll be having him later on in the festival this Thursday. He asks, there's a lot of discussion about the destabilization of the East Antarctic ice sheet, notably the Totten Glacier. Yet the cryosat imagery that you provided does not illustrate this developing loss. Is that because East Antarctic ice loss is not yet showing and mostly based on assumption? Could you talk to us about East Antarctic ice loss?
Yes, it's a very important question, because I think the evidence reveals that East Antarctica as a whole is showing a tendency to balance the losses to a certain degree in West Antarctica. Now, my sea level rise charts, which I can provide online, show that when you add up East Antarctica and offset it with the losses in West Antarctica, that they don't balance, and actually we have a net loss. That's not to say that the whole of East Antarctica is accumulating to try and compensate for the losses in the West. That's not true. There are actually some regions where we do have concerns, and Totten Glacier is picked out in the cryosat examples as being one of the basins which is declining in elevation. So it's deflating in the same way, but not quite as dramatically as the other basins like Pine Island and Thwaites. And so it's an area of concern that we're watching, but it's not contributing quite the same degree to sea level rise at the moment. Of course, that tendency might change if the processes which are undermining the ice shelves in West Antarctica similarly start to destabilize Totten, for instance. So we'll be watching it with our satellites, but it's not of as great a concern, for instance, as Thwaites, for instance, which it has the potential to unlock significant sea level rise in the future.
Thank you. We have a question now from Henry, who is 10 years old and has visited Antarctica. He says, I watched the recent launches of satellites over the polar regions by SpaceX this last weekend. Do you expect data from these to help monitor Antarctica, or do you get enough data from the satellite coverage that you have?
Well, Henry, what a fantastic experience that was, watching SpaceX launch a satellite from ESA for the first time. It was a joint endeavor with NASA, which was the reason why we launched on an American launcher. But Sentinel-6 Michael Freilich, which was the satellite we launched that day, has been designed specifically for monitoring sea level rise. Although it has the same type of instrument as some of the other ones which I've shown, like Cryosat measuring the poles, its focus is primarily on the ocean, and the inclination of the orbit means it flies largely over the oceans and not the ice caps. But nevertheless, it's working together with our polar satellites so that we can compare its information with the ice mass losses I've shown today. And it's using information like that we can calculate exactly how much the sea level's rising in response to changes in Antarctica. And so it's working hand in hand with the other satellites. And thankfully, the Sentinel-6 Michael Freilich satellite is scheduled to operate for many, many more years now. And so that gives us security that at least we're able to have the capacity to monitor sea level rise around the globe. But it's a great question. Thank you. I hope you were excited when the rocket landed as well, because that's a phenomenal experience when you actually see it in person as well. So I'm happy you watched that. It was a great event.
So we have Pierrick Senelea, who has said that the Brunt Ice Shelf has been in the news recently. There is a berg apparently the size of Greater London, which is about to break off. Can you talk about what that might mean for countries like Chile?
Well, the Brunt Ice Shelf, and certainly the portion of the ice shelf that's a concern right now, we've been monitoring for several years. This led to a number of events. Perhaps the most important event was the British Antarctic Survey, who have placed a new research station on the Brunt Ice Shelf during the recent most international polar year. They've had to move the base because of the growth of a large fracture across the ice shelf. And they towed the base based upon our satellite images to a new location so that it wouldn't separate from the ice shelf once this iceberg breaks away. Now, using the satellite images, we've been able to monitor the development of that situation. And I actually have some slides to show this, although I didn't have time today. We've been watching the propagation of a large rift and crack. But more recently, another crack has developed on the neighboring ice shelf. And so what we're expecting is potential for not only a large piece to break off from the Brunt ice shelf, but the neighboring ice shelf as well. And so there are two large pieces which we're forecasting will break free fairly soon. There's only a few kilometers left joining the Brunt ice shelf iceberg to a piece of grounded ice. And so it's very likely that these ice shelf pieces will break away as two large icebergs in the near future. Now, this has been forecast for a while. We're watching the motion of the ice shelf and the velocity of the movement of those pieces of ice, which tell us strain rates and how the pieces of ice are moving with respect to the rest of the ice shelf. But the fundamental thing is that these pieces of ice are already floating. So they already displaced their weight in water. And as a consequence, there won't be any further sea level impact from these icebergs when they break away.
Now, we haven't got a name for this question. Has precipitation increased in the Antarctic over the past 30 years?
It's been a question that scientists have asked for a long time as to whether with global warming, it may snow more over the central part of the Antarctic ice sheet, which could result obviously in a net increase in accumulation of ice mass in the central part of the ice sheet. The thing is, we've seen over the last years using precipitation modeling that in actual fact, the net mass gain in East Antarctica is not significant, and it's of the order of 5 gigatons a year by comparison to some of the figures we've been looking at in terms of hundreds of gigatons of ice mass loss. So it's barely compensating for the ice mass lost by iceberg calving and melting in the West Antarctic ice sheet at the moment. And so we don't see a significant trend which would necessarily lead us to believe that with global warming, we might see more snow on the ice sheet in general. So at the moment, it's not compensating barely enough for the ice mass losses.
We have a question from Acacia. Do the satellites assist with any data regarding the salinity of the oceans as the ice caps break and melt fresh water into salt water, and the consequent anticipated effect on weather patterns?
We've got you covered because we have a satellite called SMOS, Soil Moisture and Ocean Salinity Satellite. We've been monitoring for a decade now ocean salinity, and it's a very important question because as icebergs break off and melt, they discharge a lot of fresh water into the ocean, and this changes the distribution of salinity in the ocean. And it's a very good question because we see that that has an impact on the way in which the currents work in different parts of the ocean. Gradients and differences from one place to another in the salinity help to drive ocean circulation patterns. And so it is very important that we monitor salinity changes as a consequence of ice mass loss around Antarctica. And so, yes, we see plumes of fresh water around these areas of very dense icebergs. And of course, fresh water floats on the top of more saline water, and that also influences the way in which the heat exchange takes place between the ocean and the atmosphere. And so it's very fundamental to get complementary salinity measurements together with the other ones that I've shown, because that allows us to put the jigsaw puzzle together and address other scientific questions like how does that affect the way in which the ocean circulation works together with climate.
We have a question from Adam from Oxford. It's a political question, this. He says, it's a depressing question, but how does Brexit affect work with the European Space Agency?
I think it's a fundamental one. What I can say is the European Space Agency Convention is such that the UK will continue to play a very significant role in what we do in development of satellites. And that's not going to change because the convention for ESA is not connected to the European Union. So let's make that clear first of all. The European Union program, I think, which is important here, relates to Copernicus, and there the UK's role has been influenced by the reaction to Brexit and the necessity to arrange for a third country agreement with the European Union. Now, UK will continue to be able to play a role in Copernicus now because they are trying to establish an agreement with the European Union to continue play a role in Copernicus. And so hopefully we can continue to join everything together. UK will continue to contribute to ESA and in the context of Copernicus play a role there with some of its services, which in the polar domain is very important because the UK has a fantastic polar science community, and it would be impossible to imagine the kind of research which has been performed, which has produced the examples I've shown today. It would be impossible without the UK scientists on board. So I would like to send a strong message that we want the UK on board, and in Europe, we want UK involved in Copernicus in the future.
The European Space Agency does on-the-ground work in the Antarctic as well. There's quite a tradition of experiments being performed that can be then transferred to space. Could you talk to me a little bit about what you're doing there now?
Yes, well, I've been to both poles many times. I've wintered in Antarctica. I've been on icebreakers, and we try to make experimental evidence for what's going on in the satellite measurements by making measurements directly on the ground. And so we send scientists out into the field with instrumentation that replicate the types of measurement from the satellite. And these tell us about the fidelity of our satellite measurements. It allows us to validate what the satellites measure and to prove that in actual fact, the satellite measurement is a true representation of what's going on. So we do that in many places, and we also combine it with airborne flights with similar instrumentation to the satellite, and we try to fly beneath the satellite with people on the ground and the satellite above. That allows us to link all the measurements together, and this tells us about the uncertainties in the measurements, so we know the accuracy and the uncertainties. It tells us about where the measurements break down a little bit, and we know in quite some detail which locations are problematic and which not. And that allows us to put together some confidence in this climate record and to know how our projections are influenced by the uncertainties. So it's fundamental. We go on ships, planes, automobiles, and we do various experiments at both poles. And I have a fantastic campaigns team in my division who are responsible for organizing our experiment. And another fantastic thing we've contributed in the last year has been a Mosaic expedition in the Arctic, which is a fantastic 1 year long drift on an icebreaker in the sea ice. And there we've had various instruments making measurements throughout the year. So this is a common endeavor for us, and we're privileged to be able to operate in Antarctica together with all of the nations who are protecting the region. And we have various instrumentation also at different bases which are measuring year round. So yeah, it's an important element of what we do, and I think it's essential to ensure that people have the confidence in the satellite measurements.
Well, look, thank you so much, Dr. Mark Drinkwater. It's really been amazing to have you with us. We also know you've come here into fairly difficult circumstances, so we are so grateful that you've come through and managed to give us such an amazing talk. Anyone who wants to watch highlights of the talk again, or indeed share it with their friends, it will be on our website from tomorrow. Tomorrow evening, we will be having a talk on a topic that it particularly excites us at Shackleton, ice memory, or what can be found out about the Earth's past from bubbles trapped in ancient ice. Dr. Mackenzie Greenman of the University of Cambridge will be here to give that talk. She'll be here from 6 p.m, so we hope to see you there. Goodbye.